Description of our module: subject name physics, paper name quantum mechanics, title a brief review of foundation of quantum mechanics. There are some contents of our module. First content is inadequacy of classical mechanics, chronological development of quantum mechanics, Planck's theory of blackbody radiation, photoelectric effect, Compton effect, Bohr atomic model, De-Broglie hypothesis, Heisenberg uncertainty principle, and last content is Schrodinger wave equation. Learning outcomes from this module are failures of classical mechanics, quantized energy of electromagnetic radiation, Einstein's explanation of photoelectric effect, particle behavior of X-rays, matter wave, and Schrodinger equation. Now, first content of our module is inadequacy of classical mechanics. Classical mechanics is based on Newton's three laws: first law of inertia, the second law of force, and third one, the law of action and reaction. These laws include the concept of absolute mass, absolute space, and absolute time. The classical mechanics explain the motion of celestial bodies like planets, stars, and macroscopic as well as microscopic terrestrial bodies moving with non-relativistic speed. The inadequacies of classical mechanics are: first one is it cannot explain the relativist non-relativistic motion of atom, electron, proton, etc. It could not explain the stability of atom. It could not explain spectrum of blackbody radiation. It could not explain the various variation of specific heat of metal and gases. It could not explain various observed phenomena like photoelectric effect, Compton effect, Raman effect, Zeeman effect, etc. The inadequacy of classical mechanics lead to the development of quantum mechanics. Rayleigh's energy density distribution. Rayleigh-Jeans formula. Rayleigh gave a formulation for blackbody radiation. This formula agrees with the experimental result at longer wavelength only, not at shorter wavelength. As we move towards shorter wavelength or higher frequency, as you can see in this diagram, value of energy would increase without limit, whereas experimentally it must be finite. The integration of this equation over all frequencies diverge implies that the cavity contains an infinite amount of energy. Divergence of this equation for higher frequencies or shorter wavelength, that is in the ultraviolet range, is called ultraviolet catastrophe. It's very important. This was a classical prediction first made in the late 19th century that an ideal black body at thermal equilibrium will emit radiation with infinite power. It is a real catastrophical failure of classical physics. As we can see in the graph, Planck's 1900 introduced entirely new idea to explain the distribution of energy. You can see in this diagram there is a complete agreement with the experimental result of at all wavelength. Planck's energy distribution. The problem of ultraviolet catastrophe has been resolved by Max Planck. An accurate description of blackbody radiation has been put forward accordingly. Planck considered that the energy exchange between radiation and matter must be discrete, not continuous. He derived a radiation law by using the following assumption. Assumptions are: first one is a blackbody chamber is filled up not only with radiation but also with simple harmonic oscillator or harmonic oscillator or resonators. You can say resonators of molecular dimension. They can vibrate with all possible frequencies. Second one is the frequency of radiation emitted by an oscillator is the same as the frequency of its vibration. An oscillator cannot emit energy in continuous manner. It can emit energy in the multiples of the small unit called quanta or photon. Planck postulated the energy of the radiation emitted by charge, oscillating charges must come only in integral multiple of h nu. Here value of energy is E is equal to n h nu. N is 1, 2, 3, it's an integer number where h is universal constant and h nu is energy of quanta of radiation. E is equal to n h nu is known as Planck's quantization rule of energy or Planck's postulate. Here, so the energy density per unit frequency of radiation emitted from whole of a cavity is given by this expression. This is known as Planck's distribution relation. This relation can be rewritten in the terms of wavelength. So, the Planck's energy density per unit wavelength can be written as, here h is Planck's constant, c speed of light, lambda wavelength, k Boltzmann constant, these are the values, and T temperature in Kelvin. The introduction of the constant h had indeed heralded the end of the classical physics. The dawn of the new concept, the micro-physical world, namely quantum mechanics, assuming that the energy of an oscillator is quantized. After then, photoelectric effect. This is our next content of our module. The photoelectric effect provides a direct confirmation for energy quantization of energy. Light. Photoelectric effect first noted by Hertz in 1887. This is the pre-electron phenomena. After then, characterized by Lenard in 1902. The photoelectric effect is a phenomena in which electrons are ejected from the surface of the metal when light is incident on it. These ejected electrons are called photoelectrons. Increasing the intensity of light increase the number of photoelectrons but not their energy. Characteristics of photoelectric effect. There are some characteristics of photoelectric effect. First one is effect of intensity. Intensity of incident light affects the photoelectric current. If the intensity of given frequency increases, the number of photons strike on the metal will increase. Hence, more electron ejects from per unit area of metal surface, giving rise to an increase in photoelectric current. Here you can see, as we go towards the higher intensity, the value of photoelectric current increases. Effect of frequency. The frequency affects the maximum kinetic energy or stopping potential of photoelectrons but leaves the photoelectric current unchanged. You can see here, as we go towards the higher frequency, value of retarding potential increases, means value of kinetic energy also increases. Effect of metal. Photoelectric current depends on metal used because threshold frequency, minimum frequency to eject out the electron from metal are different for different metals. The slope for all metals is same, and hence this is the universal constant. Effect of time. There is no time lag between the incidence light and emission of photoelectron. As the radiation fall on the surface of metal, electron start ejection of electron starts immediately. Okay. In 1905, photoelectric emission was successfully explained by Albert Einstein. With the help of Planck's quantum theory, he proposed that light consisted of quanta called photon. Each incident photon has energy is equal to h nu. He got Nobel Prize for this. Einstein's explanation of photoelectric effect. Accordingly, if h nu is the energy of incident photon, then the kinetic energy of ejected photoelectron is given by Einstein's photoelectric equation. This is the energy of incident radiation, work function, and kinetic energy of photon. Energy of photon used up in two ways. A part of it used to eject out electron from metal surface, and remaining energy of photon is impart kinetic energy to the electron. The minimum energy required to liberate electron from the metal surface is called work function. You can see here. Depending upon the threshold frequency of the metal. The stopping potential is, the value of stopping potential is this. Negative potential of the collector. What is the stopping potential? Negative potential of the collector plate at which photoelectron current is 0. Here the magnitude of the photoelectric current thus generated is proportional to the intensity of the incident radiation. The speed of electron does not depend on the radiation's intensity but on its frequency. Means speed of electron depends on frequency only, not on the intensity of incident light. In nutshell, the photoelectric effect does provide compelling evidence for the corpuscular nature of the electromagnetic radiation. The photoelectric effect provides evidence for the particle nature of the light. Okay, other content of our module is Compton effect. Compton also provided the most conclusive confirmation of the particle aspect of the radiation. Compton effect is a process in which X-ray collides with the electron and are scattered. You can see here there is electron. This is the incident radiation. Here photon strike with it and scattered with higher wavelength, and here electron is recoiled. X-ray lost frequency of interaction with material. Wavelength of scattered radiation is larger than the wavelength of the incident radiation. A part of energy transferred to the recoiling electron. Classically, there would have been no frequency shift. Confirmed photon theory. Wavelength of scattered radiation does not depend on the intensity of incident radiation. It depends on the angle of scattering and wavelength of incident beam. Here theta is angle of scattering. The wavelength of the radiation scattered at angle theta is given by this, where m is the rest mass of electron and constant h upon mc is known as the Compton effect of the electron, and it has the value 0.0024 nanometer. Delta lambda is called wavelength shift, means difference between initial wavelength and final wavelength. This relation, which connects the initial and final wavelength of scattering angle, confirms Compton's experimental observation. The wavelength shift of X-rays depend only on the angle at which they scattered and not on the incident photon. Compton effect thus confirms that photons behave like particles. They collide with electron like material particle. Another content of our module is Bohr atomic model. When an electron moves in its stationary orbit, the emission or absorption of energy takes place. When an electron jumps from one orbit to another, this emitted and absorbed energy is quantized. Okay, there are four postulates of Bohr atomic model, but we focus on the third postulate. Third postulate comes from the quantization of energy of electromagnetic radiation. You can see here, electron jumps from N1 shell to N2 shell by emitting some energy. H is equal to h nu. This energy is quantized. Okay, there was some issue. Let's start. Our next content of our module is De Broglie hypothesis. Before understanding De Broglie hypothesis, we focus on some points. First one, Newton thought light consisted of corpuscles. Huygens believed that it was a wave. By the end of 19th century, everyone knew it was a wave. Young's slit. By the experiment of Young's slit. Photoelectric effect and Compton effect. These are the phenomena which confirms the particle behavior of the radiation. Bohr atomic model is also confirms that electromagnetic radiation is quantized. It was impossible to observe both the wave and particle aspects simultaneously. Then, in 1924, De Broglie proposed a hypothesis. According to De Broglie, every moving particle has a wave associated with it. The De Broglie wavelength of a particle depends on its momentum. According to the De Broglie relation, particle wavelength is lambda is equal to h by p, lambda is equal to h by m v, where m is mass of particle and v is velocity of particle. This shows that wavelength of a particle can be altered by changing its velocity. Means if you change the velocity of a particle, its wavelength will automatically change. So for an electron, expression can be written as. In 1929, De Broglie was awarded the Nobel Prize in Physics for his discovery of wave nature of electron. Important point, De Broglie hypothesis is applicable only for microscopic particles, not for macroscopic particles. After then, in 1927, a German physicist, Heisenberg, gave a principle. This was that was the most important contribution in quantum mechanics. Heisenberg uncertainty is also a fundamental concept of quantum mechanics. In 1927, German physicist Heisenberg formulated a uncertainty principle which stated that we cannot determine both the position and momentum of a particle simultaneously with perfect accuracy. We can understand it like this: the more we nail down the particle's position, the less we know about its momentum. It is represented, sorry, this is missing, delta x dot delta p greater than and equal to h upon 2 pi. Schrodinger equation. After then, Schrodinger equation came in picture, but before understanding it, we have to understand some important points, some important things. Basically, before 1926, all atomic model we have studied, like plum pudding model, Rutherford model, atomic model, and Bohr atomic model, were based on particle behavior of electromagnetic radiation. According to Bohr model, electron moves around the nucleus in its stationary orbit, but according to De-Broglie, every moving particle has a wave associated with it called matter wave. It means, according to Heisenberg uncertainty principle, it is impossible to determine the exact position and momentum of electron simultaneously. Electrons move with fixed velocity in its stationary orbit. As you know, momentum is quantized. It means it is impossible to determine exact position of electron on its stationary orbit. Now in 1926, quantum mechanical model of atom came in picture, given by Schrodinger. He agreed with Heisenberg and said that if it is impossible to find exact position of electron, but it is possible to calculate the probability to find out maximum number of electron in particular three-dimensional region. This is called orbital. He gave a wave function for three-dimensional wave associated with moving electron. It can be represented by psi. You can see here psi represent a maximum amplitude of matter wave associated with a moving electron. You can see here psi represent the maximum amplitude. But we can see in graph there is a negative value of psi here. There is a negative value of psi also. But we also know that probability can never be negative. It means there is no significance of psi, such as no significance of -1 under square root. Then Schrodinger introduced a new term psi square. This is the probability to find out the electron in per unit volume. Thus Schrodinger equation came in picture. You can see here psi square probability, graph between probability to find out the electron in per unit volume, and distance from nucleus of the electron. Thus, Schrodinger equation came in picture. H psi is equal to E psi. H is Hamiltonian operator. E total energy of the system. That was the beginning of new quantum mechanics. Two equations given by most important equations given by Schrodinger are time dependent Schrodinger equation and time independent Schrodinger equation. We will discuss about these in our next module. Here is quiz. You can solve it. There are some questions, basic questions, conceptual questions. Thank you.